So if I'm adding mean 1, mean 2, mean 3, mean up to mean n, then I'm just going to have n times the means. We are assuming that the mean from each of these these random variables is the same. So the mean for this random variable is the same as this one, is the same as this one. So we sum them and we get this. The variance we do the same and we get that. So a plus a plus a plus a plus a will give you na. A times a will give you a squared. So don't a times a up to n a's will give you a to the power n. So don't confuse them. When you are adding, you have n of what you are adding. If you are multiplying, you have what you are multiplying to the power, the number you are multiplying, the number of times you are multiplying it. So in general, if we are summing the random variables, then we are just going to have the summation of the random variables to be distributed as normal with mean n mu and then variance n times the sigma squared. But we are talking about the mean. We want the mean of the random variables, not the random variable itself. We want its mean. So what that means is that simply I'll divide this here by n, and then I'll divide this one by n. And because this is a variance, I'm going to divide by n squared. Now, if I do that, this is what I'm going to get. Because I'm dividing the n mu by n, the n will cancel n, so it will just leave with only this one. And for the variance, because I'm having a variance, so I have to square, so it's going to be 1 over n squared, but it's just the same as 1 over n squared. So I'm just going to have n times the variance square, the sigma square, divide by n squared. So the n squared will cancel this n here, leaving 1n. So you are going to have variance over n. So this time around, so the mean of the random variable is going to be the mean, but the variance is no longer just only sigma square, but it is sigma square over n. Another way you can write this thing here is to take square root on it. So when you take square root on the whole of this, then the square of the variance will cancel the root, leaving only the root on the end. So we can conclude that the mean of the random variable is normally distributed with mean and then variance sigma over square root of n. So if we want to find our z here, we are no longer going to use we are no longer going to say x minus mean over the standard deviation, but it is going to be over the standard deviation over square root of n. Now let's take this data set. Let's take this data set. We are going to look at, or we are going to learn how to differentiate between point estimate and then interval estimation. So let's consider a study where we want to estimate how long it takes us to walk to the university. And you are saying that the population standard deviation is 1.4. You know the population standard deviation. Now, let's compute the mean of the data. So you decide to use your stopwatch or maybe your phone to record the number of times you walk to the university, to record the time it takes you to walk to the university. So the first day you recorded 17.2 minutes, the second day 18.3 minutes, up to the last day 16.5 minutes. So you decided to do this for 40 days. You can do for 50 days, you can do for 60 days, depending on how much time you have, you can do this. So to find the mean, we sum the data values and divide by 40, just like we did when we were doing the descriptive statistics. So if we do that, the mean is going to be 17.76, approximately 18. So what this is saying is that on average, it will take you 18 minutes to walk to the university. On average, it will take you 18 minutes, approximately 18 minutes to walk to the university. The question we are asking ourselves is, Can we generalize this? Can we use this to say that, oh, in general, for anyone to walk to the university from here to the university, you are going to spend 18 minutes. Can we generalize that? Now we need to check whether this is acceptable or it is not acceptable. Can we generalize this? Can this represent our population? Is the mean actually the true mean, or there are values in the data that have influenced this value that it cannot represent the population? So how do we do that? To do that, we need to construct a range of values for the mean so that we can say that the mean is between this value and this value, so that you can say that, oh, the time that you need to spend to walk to the university is between maybe 10 minutes to 15 minutes, or maybe 11 minutes to 15 minutes. We want to be able to say that. So now we are dealing with interval here. So we are going to create an interval where we can say that, oh, within this interval, that is the time that it will take you to walk to the university. Maybe you may not be able to give exact, Leonard, you are raising your hand. Is there any problem?
No, sir, please, it was a mistake.
So we need to be able to say that, we know that the value or the time it will take for you to walk from this point to the university is 18 minutes, or is between this point and that point. We want to create a lower point and an upper point so that we can say that the average walking time to the university is between these values. And when we do that, we call that interval estimation. So the point estimation, we just compute the mean and that is it. We compute the variance and that is it. Now we want to create an interval defining the mean, and that is what we call interval estimation. And when we are doing the interval estimation, we want to also be able to say that we are 95% confident that the mean is between here, because you will tell someone that, oh, to walk to this particular point, you need 5 minutes. And the person will ask you, are you sure? So we want to be able to say that, yes, we are 95% sure. We are 99% sure. We are 97% sure. We want to say, we'll be able to say that we are 95% sure that, yes, the average time it will take you to walk from this point to the university is between this interval. We want to say that. So, because we are now dealing with the mean, we are now dealing with the mean. Oh, come on, this thing. We are dealing with the mean here. So you can see that we are repeating ourselves here. The mean is normally distributed with mean and then standard deviation. Remember the previous definition of the Z. The previous definition of the Z was C, X minus the mean over the standard deviation. And we did this because the X was normally distributed with mean, and then the variance is here, so the standard deviation will be just sigma. But this time it's not longer the case. We now have our mean to be distributed as mean and then sigma over root of n. So what that means is that we are going to have the X, which is the mean. So remember the previous one was just X. So we take the X minus the mean. This time we are taking the mean of the sample minus the population mean, divide that by the standard deviation from the population, divide by square root of n. Now, how do we create the interval? To create the 95% confidence interval, we need to read a probability. So we are saying that we are committing 95% error. We are 95% confident that the interval will contain the mean. So what that means is that we are making 5% error. So with 95% confidence interval, what we are simply saying is that the Z is between negative 1.96 and 1.96. These values are also read from the Z table. So the probability to read is 0.95. So when we meet face to face, I will use those books to show you how to read. If you have a probability of 95%, how do I get the corresponding Z values? When we meet face to face next week, I will bring the book and then I will show you how to read these values. Because if you are going to do this in the exam, it is those books that you use in the exam. So it is important we use them to do the illustration. So in our face-to-face meeting, I will show you one of the books and then how you read the values from them. So we have this. Now, the Z. So we are saying that the Z is between negative 1.96 and then positive 1.96. But we know that the Z is equal to this guy here. The Z is equal to this. So we substitute in place of Z, we put this one. And then we multiply this one by sigma over root of n. And that is why we have that one here. We are multiplying this part here by here, and then we also multiply that by here. So we are going to multiply that. So when we do that, this is what we get. And then we do that, that is what we get. And then the X, we take X across so that we have X bar minus what we have here. And then we take the X also across, and then we get X bar plus 1.96 multiplied by sigma over square root of n. This is our interval. So this part, the whole of this part where you have the plus is the upper limit or the upper value, and the one with the negative here is the lower. So you can see that you are subtracting the same thing from the mean. So you subtract this value from the mean and you add that value to the mean. So you create an interval for the lower and for the upper limit. So if I know my mean for the sample and I know the standard deviation for the population and I know the number of data points that I've used from the sample, then I should be able to find my confidence interval. So the confidence interval is going to be X minus this, comma, and then X plus that. So this is the lower limit or the lower, the lower part or the lower limit, and this is the upper part or the upper limit. So we can use our working time data. So when we look at the working time data, our mean was 17.76 with population standard deviation 1.4. So we substitute that. The number of observations is 40. So we substitute that. So we have 17.76 minus 1.96 multiplied by the standard deviation, which is 1.4, divided by square root of 40. Then you do the same for the other side, but you add. And when you solve that, you are going to get 17.33 and then 18.19. So you have to ask yourself, is the mean in the interval? That is what you have to ask yourself. This interval, does it contain the mean or not? So you can see that the mean is 17.76. And that contains the mean because 17.76 is inside the interval here. So the interval contains the true mean. So that means that the mean represents the population. If the mean does not represent the population, the confidence interval will not capture it. So we can say that the sample that we can use it to generalize that the average time it takes to walk from this point to the university is 17.76 or approximately 18 minutes. But how confident are we? So this time we can say that we are 95% confident that the confidence interval contains the true value, or we are 95% confident that the average time it will take you to walk from this point to the university is between 17.33, and 18.9 minutes. That is all. So depending on the percentage of confidence that you want to find, depending on the percentage of confidence that you want to find, then you will read from the table here. So if you are doing for 90%, you read. If you are doing for 55%, you read. If you are doing for 98%, 99%, and so on. So this is what we have. So if I know the percentage of confidence I want to use, I can read my corresponding Z value as here. So if I know my mean, I substitute it. I go to the table, read my Z value. If I'm using 90%, substitute that. My population standard deviation, I will substitute that. And then I know my N, I substitute that. When I get the value, I subtract it from X, from the mean of the sample, and then I add it to the mean of the sample. And that will give me my confidence interval. So here is another example where you want to estimate the mean weight of animals. And you consider 47 of the animals. You randomly selected them. You don't go and pick those animals you like. You randomly select and weigh the animals. And when you weigh the 47 animals, you realize that the mean weight is 6.7 kilograms. And you know that the population standard deviation is 1.7. So you know the population standard deviation. You also know the sample mean. You know your N to be 47. Go and substitute it into the confidence interval formula. And we are dealing with 95 here. So the 95, we use our 1.96. So 6.73 minus 1.96 times our standard deviation, which is 1.7, divided by the square root of N, which is 47. So you compute this one here. When you get the value, subtract it from 6.73, and then you add it to 6.73, and that gives you your interval. So when you do that, the interval is this. Now you ask yourself, is the mean, which is 6.73, inside this interval? Of course, yes. 6.73 is inside this interval. So we are 95% confident or sure that, yes, our interval contains the true mean. And so therefore, we can use this mean to generalize that the mean weight of the animals is between 6.24 and 7.22, or the mean weight of the animals is 6.7. So you can do for the 99% confidence interval. So if you are going to do for the 99% confidence interval, you come to this table. So you are no longer going to use 1.96, but you are going to use 2.58. So wherever you see 1.96, you substitute 2.58 there. And then you substitute 2.58 here. And then you solve and see whether your interval will contain the true mean or not. Now, we all know that when you increase the amount of information that you give, if you increase the amount of information that you give, then you are likely to approach or to get the true answer. If I'm showing you a direction and I'm unable to give you enough information, definitely you will not be able to get to where you want to go to. It's the same thing when we are estimating the mean. We are worried about how much information should we gather before we can get a mean that will represent the population. What is the sample size that we should use? Should we use 30? Should we use 40? Should we use 50? Should we use 70? We don't know. So there is a need to determine sample size that will be able to reflect the population. If you have 100 people you want to study, and you want to take only 10 of them to do your studies, will the information from the 10 people be enough for you to generalize on the entire population? Maybe not. So we determine the sample size. So to determine the sample size, we have to ask ourselves, what is the margin of error that we are going to make? And we have to know the significance level also. So to do that, we consider this example. And on this example, we are saying that a rugby coach of under 19 team is interested in the average mass of 18-year-old males. So we are interested in the average mass. And we know the population standard deviation to be 6.58. Now, what is the sample size? What sample size do we need in order to be 95% sure to obtain an interval average of mass of 18-year-old males within 2 kilograms of the true value? So what this is simply saying is that, okay, we are getting the mean. So how are we going to be sure that we are just getting the mean that is 2 away from the true mean and then 2 above the true mean? So the mean is x bar minus 2, which is the error margin, and then x bar plus 2, which is the error margin. Remember, in the confidence interval, the error part of the confidence interval is this part here. You can see this part is the part that we are subtracting from the mean. It's the same part that we are adding to the mean. So if at all there is going to be any error in the mean, it is going to be coming from this part. So the error part is here. We are adding it, we are subtracting it from the mean, and we are adding it to the mean. So you can see that x bar minus this, and then x bar plus this. So this is just the same thing as the 2. So you can see that the whole of this is equal to the 2. The whole of that is, so you see we have x bar minus 2. And here we have x bar minus this guy here. So the whole of what we have here is equal to 2. So the whole of that is equal to 2. But we are dealing with 95% confidence interval. So our confidence interval is going to be x bar minus 1.96 sigma over square root of n. So this is the error. So our 2 is going to be equals to 1.96 is going to be this component here. So we have 2 to be equals to 1.96 multiplied by our standard deviation, which is 6.58, divided by the square root of our n. But remember, we are interested in finding n, so we have to make n the subject. What that means is that we'll multiply both sides by square root of n. So we multiply 2 by square root of n, and we multiply the right-hand side by square root of n. So square root of n will cancel the square root of n that will multiply. So here we are going to have 2 times the square root of n. 2 times the square root of n. But we don't want the square in the n. So first we divide both sides by 2. And that is what we have here. And then we square the root, and that is what we have here. So our n is going to be equals to 1.96 multiplied by 6.58 divided by 2, all to the power 2. And if we do that, we are going to get 42. So we need 42 sample size to be able to be sure that then the interval will contain the true mean, or the sample that the information that we will get from this sample will represent the entirety. So that means we can generalize the formula for the sample size computation. How do we do that? So that means our n, that is the sample size, is going to be equal to our z value. So remember the z value was the 1.96 multiplied by the standard deviation. So that is the standard deviation here, divide by 2. But remember that 2 was the margin of the error, which was given here. And so we represent that by L, the length, and that is this. And then we square all of that. So when you want to find the sample size, what are you looking for? You want to know what percentage of confidence are you computing, and then you read that from the table and substitute it. What is the standard deviation for the population? You will be given that value, and then you substitute that. What is the length of the margin? How far away from the mean? Then we substitute that value in place of n. And then we find our sample size, and that is that. Any question? Any question? Any question?
No, please.
All right, our time is up. 8:54. So we are supposed to end our lecture here. So next week, in our face-to-face meeting, we will start hypothesis testing. I want us to finish this. We are going to use 1 hour time to solve the questions that we have in the handbook. We'll solve the questions in the handbook. They are not difficult. So with 1 hour, we'll be able to solve all the questions in the handbook. So we will have our face-to-face meeting. And then in 2 weeks time, then we have we have the tutorials. So next week we'll have our face-to-face meeting. In the other week, then we'll have a tutorial for 1 hour. So we'll use the face-to-face meeting for the tutorial. Any question? Any question?
No question.
Okay, so we end our lecture here. Our next meeting will be on hypothesis testing. Okay, bye-bye. I'll send you the slides. I'll send you the record, the recordings of this meeting. I'll send it to you over. I'll share it via the YouTube channel so that you can watch that.
Yes, sir.